So the title of my talk is Subexponential Parameterized Algorithms for Hitting Subgraphs. So let's start with a general class of problems in algorithmic graph theory. So this class is called vertex deletion problems. So in such problems, we are given a graph G in some graph class G, and also an integer k, which is a parameter. And our goal is to compute a subset of vertices of the graph S, such that that subset only contains at most k vertices, and the graph G minus S satisfies a certain probability P. So here, the graph G minus S is just the graph obtained from G by removing the vertices in S and the edges incident to these vertices. Okay, so in most of the vertex deletion problems, the probability P considered is subgraph closed in the following sense. So if a graph G satisfies P, then all subgraphs of G also satisfy P. So when this probability is true, we say the probability P is subgraph closed. So when we consider a vertex deletion problem with a subgraph closed probability, then we have an equivalent formulation for the problem as follows. So the vertex deletion problem can be equivalently expressed as computing a subset of vertices S of size at most k, such that G minus S does not contain any graph in F as a subgraph, where the set F is a set consists of or minimal graphs that do not satisfy the probability P. So as you can see, so if P is subgraph closed, then G minus S satisfies P if and only if it does not contain any graph in F as a subgraph. So in this formulation, we can view F as a set of forbidden patterns, and our goal is just to hit those forbidden patterns in the input graph using at most k vertices. So in other words, the vertex deletion problem becomes a hitting set problem. So this formulates the problem F hitting, which is the problem studied in our work. So formally, we let F be a fixed set of graphs. And the F hitting problem on a graph class G is defined as follows. The input is just a graph belonging to this graph class and a parameter k, which is an integer. And we just want to compute a subset of size at most k of vertices of G, such that if you remove those vertices from your graph, the remaining graph does not contain any graph in F as a subgraph. And it is easy to see that if F is an infinite set, then this F hitting problem might be hard even when k is equal to 0. In the case k equals to 0, the problem is nothing but detecting whether the graph G contains any graph in F as a subgraph or not. So when F is infinite, even this problem can be hard. Therefore, in our work, we mainly focus on the case when F is a finite set. Even though we assumed F is finite, the F hitting problem still generalizes a lot of fundamental vertex deletion problems. Here, let me list some examples. So the first one is vertex cover, which is in this problem, you want to remove k vertices from the graph such that the remaining graph has no edges. Then if your set F consists of one graph with two vertices connected by an edge, then the F-hitting problem is just vertex cover. And the second one is path transversal, where we want to hit all paths in the graph of certain length using at most k vertices. Of course, this is a F-hitting problem. And similarly, we can define short cycle hitting, where our goal is to hit cycles of a certain length. And there is another problem called degree modulator. Here we want to remove k vertices from your graph such that the remaining graph has degree at most at most c, where c is some fixed constant. So here, to see why this is a F-hitting problem, we can define F as a set only consisting of one graph, which is a star with a center vertex and a c+1 vertices connecting to it. And another problem is the so-called component order connectivity. In this problem, we want to remove k vertices from the graph such that the remaining every connected component of the remaining graph has size at most c. So here you only need to define F as the set consisting of all connected graphs of size c+1, then the F-hitting problem is equivalent to component order connectivity. And also there is another problem called tree depth modulator. Here you want to delete k vertices from your graph to make the remaining graph has tree depths at most c. It was known that this problem can also be formulated as a F-hitting problem. And there are many other examples as well. So the F-hitting problem is known to be FPT, fixed parameter tractable, for any finite f. And in fact, it was known that for any fixed finite set f, the F-hitting problem on any graph class G can be solved in 2 to the big O of k times poly n time, where n is the number of vertices of G. And this is not very difficult to prove. So it's proved using the following branching algorithm. So we suppose like we want to solve the problem on G with budget k. If the budget k is already smaller than 0, then we just return null. We don't have any solution. And otherwise, we try to find a subgraph H of G that is isomorphic to some graph F in our set F. Of course, if such a graph does not exist, then we don't need to delete anything. So if such a graph exists, then we know that at least one of the vertices of this graph should be included in our solution. Then we just try every possibility. We consider every vertex of this subgraph and try to include in our solution. So if we include it in our solution, then the remaining problem becomes G minus V with budget k minus 1. And if we can compute a solution for this this instance, then together with V, we obtain a solution for the instance GK. And as you can see, this simple recursive algorithm solves the problem. And if you observe the recursion tree, you will see the height of the recursion tree is at most k, and the branching factor of the recursion tree is a constant because f is a fixed set. And therefore, the running time of this recursive algorithm is 2 to the big O of k times poly n. So because we now know that f hitting can be solved in 2 to the big O of k time, then a natural question is, can we solve f hitting even faster in sub-exponential FPT time? But we see that if the input graph is a general graph, the answer is actually no. So there is such a famous result saying that for every non-trivial f, one cannot solve f hitting in 2 to the small o of k times poly n time, or even 2 to the small o of n time, when G consists of all graphs. In other words, when the input graph G is a general graph. And this is true assuming the ETH. Of course, at that time, ETH has not been established. But what I meant here is their reduction implies that, assuming ETH, you cannot have such algorithms. Here, the set F is non-trivial, means like there are infinitely many graphs that do not contain any graphs in F as a subgraph. Notice that if F is trivial, in other words, if there are only a finite number of graphs that do not contain any graphs in F as a subgraph, then the problem is actually, the F hitting problem is actually polynomial time solvable. Okay, so because we already know the problem is hard to solve in sub-exponential FPT time on general graphs, then the next question is, what about restrictive graph classes? We can what we have known is applying Baker's technique, and also with other ideas, one can solve f hitting on planar graphs and also unit disk graphs in 2 to the big O of a square root of k times n time for any fixed finite set f. And here, planar graph is just a graph which can be drawn in the plane without edge crossing. And a unit disk graph is a graph defined by a set of unit disks in the plane. Those unit disks are the vertices of the graph. And if two unit disks intersects, you connect an edge between those two unit disks. Okay, so this is what was known prior to our work. And in our new work, we give a general algorithmic framework for F hitting that gives sub-exponential FPT time algorithms on almost all common graph classes on which sub-exponential algorithms have been well studied. So this is much beyond planar graphs and unit disk graphs. So in order to define such graph classes, we need a notion called separator. And this is actually a well-studied notion. A balanced separator of a graph G is just a subset of vertices such that if you remove that subset T, and every connected component of the remaining graph contains at most half of the vertices in the original graph. So for example, here, if you remove T, suppose you have 3 connected components in G minus T, A, B, C, then if their size are all smaller than or equal to 1/2 times the number of vertices of G, then we say T is a balanced separator. And then we say a graph G is eta row separable if every subgraph H of G has a balanced separator of size eta times the size of H to the power row. So as you can see here, if the number row is greater than or equal to 1, then the eta row separable graphs are not interesting because they are essentially just general graphs. Every graph has a 1/2 1. Every graph is a 1/2 1 separable. You can just arbitrarily take half of its vertices, then it's a balanced separator. So the interesting case is when row is smaller than 1. In this case, if a graph class consists of only eta row separable graphs with row smaller than 1, then these graphs are of sublinear size separators, and they are also known as graph classes of polynomial expansion, which subsumes a lot of graph classes. For example, a famous example is planar graphs and its generalization, bounded genus graphs, and also its further generalization, H minor free graphs. All of these graphs admit sublinear size separator, and therefore they are eta row separable for some row smaller than 1. And it was also known that the k nearest neighbor graph in a fixed dimension admits sublinear size balanced separator, and also the greedy Euclidean spanners has sublinear size separators. So all of these graphs belong to eta row separable graphs for row smaller than 1. However, as we can see, the aforementioned graph class, union disk graphs, do not belong to this category. This is because union disk graphs cannot admit sublinear separators because they can contain large cliques. So if you have a lot of disks, union disks stacked at one position, then they form a large clique. So you cannot hope these graphs to have sublinear separators. So in order to make the graph classes, including union disk graphs and also other graph classes, we need to generalize our definition for separable graphs a little bit. So now we say a graph is eta mu row separable. So we have 3 parameters now. If every subgraph H of G has a balanced separator of size eta times omega of H to the mu and the size of H to the power rho. Here, omega of H is the size of a maximum clique in H. So in other words, we want the separator size to be sublinear in the total number of vertices of the graph and the polynomial in the size of maximum clique in the graph. So if we look at eta mu row separable graphs with row smaller than 1, then they in addition include union disk graphs or even general disk graphs or even pseudo disk graphs, which is a further generalization of disk graphs. And also they include many geometric intersection graphs in a fixed dimension. Those are intersection graphs of fat geometric objects. Okay, so now let's define G of eta mu row as the class of all eta mu row separable graphs. And we see that G eta mu row with row smaller than 1 contains all graph classes of polynomial expansion. Those are graph classes which admit sublinear size separators. And it also contains a large fraction of geometric intersection graphs. And as we will see, our result applies to all such graph classes with row smaller than 1. In fact, our result is more general, which not only works for F-hitting, but also works for a generalization of F-hitting, which we call weighted case of a F-hitting problem. Here, the given graph G has weights on its vertices. So we are given together with G a weight function on its vertices. And our goal is not only to find a subset S, but also find a minimum weight subset S under the weight function W of size at most K, such that G minus S does not contain any graph in F as a subgraph. And this is our main result. So for any graph, for any row smaller than 1, and any graph class, which is a subset of G eta mu rho, so we show that for any finite set F, there exists a constant C strictly smaller than 1, such that weighted F-hitting on G can be solved in 2 to the big O of K to the C times N plus big O of M time. Here, N is the number of vertices in the graph, and M is the number of edges in the graph. So as you can see, our algorithms runs in sub-exponential time in K, and also linear time in the size of the input graph. Okay, so to prove such a theorem, our algorithm consists of 3 main steps. In the first main step, we use some reduction rule to reduce the graph size to polynomial in K. And this reduction can be done in linear time in N and N. And after that, our second step, which is the main step of our algorithm, reduces the F-hitting instance to a sub-exponential number of general hitting set instances whose Geifman graphs are of a tree width sublinear in K. And we will explain what are the Geifman graphs of those hitting set instances. And then in step 3, we just solve each general hitting set instance in sub-exponential time. And in all of these 3 steps, we used a lot of building blocks, such as sunflowers and the sunflower lemma, tree decompositions and tree with sparse graph theory, and some techniques for hitting set problems. So as I mentioned here, step 2 is our main steps, and this is the main theorem for step 2. So we show that there exists some constant C smaller than 1, such that if you are given a graph G with n vertices and a number K, then one can construct n to the big O of K to the C in n to the big O of K to the C time, T collections of subsets of the vertices of G, x1 up to xt. And this T, you can see it's sub-exponential in K. And these T collections satisfy the following condition. So first, if you have a subset S, then it is a feasible solution for the F-hitting problem if and only if the size of S is at most K, and S is a hitting set for each of the xi here. So as you can see, with this property, you actually reduce the F-hitting problem on G to hitting set problem on x1 up to xt. Okay, then the second property says that the Geifman graph of each xi has tree width at most k to the c. Therefore, its tree width is sublinear in K. And what is the Geifman graph? So suppose now you have a collection of subsets of VG, and suppose here U is the set U is just VG, and you have a collection of subsets of U. Then the Geifman graph of this collection is defined as follows. The vertices of the Geifman graph is just the set U. In our case, is just the set VG. And then for each of the sets in your collection, we add edges between every pair of vertices in that set to make that subset a clique. So here, for example, we make this red subset a clique. And for the yellow set, we also add edges to make it a clique. For this blue set, we also add edges to make it a clique. Then after we do this, we obtain a graph, and this is just the Geifman graph of your collection of subsets. And then the second property says that the Geifman graph of each xi here has tree width at most some sublinear function of k. And then this guarantees that the hitting set instance, each hitting set instance can be solved in sub-exponential time in K using the standard dynamic programming algorithm on bounded tree width graphs. Okay, so but step 2 is the algorithm of step 2 is very complicated. It is a complicated branching algorithm. So this is the entire algorithm. I'm not going to discuss this in detail because of the time constraint. Okay, so finally, let's pose some open questions. The first open question is F-hitting problem with other parameters. We only studied the problem with solution size parameter K, but there are also some other parameters which can be studied. For example, the tree width of the input graph G, and so forth. And the second open problem is can we achieve similar results on other related problems, such as induced F-hitting? So here the problem is to remove k vertices such that the remaining graph does not contain any graph in F as an induced subgraph. And it is strictly more difficult than the F-hitting problem. And the third open problem is can we, instead of hitting all subgraphs in F in our input graph, can we hit a selected subgraph of so we are given the set F, and we don't want to hit all subgraphs in G isomorphic to some graphs in F, right? So here we want to only hit a selected subset of those subgraphs in our graph. Can we still achieve similar results? This is actually more difficult than the problem studied in our work. Okay, so this is my talk. Thank you.